Humanity has been chasing limitless energy for decades, and nuclear fusion might finally be the answer. This isn't just a new power plant or another solar panel. Fusion promises almost infinite energy with zero carbon emissions, no dangerous waste, and the potential to power the planet for centuries. If it works, it will completely reshape economies, industries, and even geopolitics. In this video, we're breaking down why nuclear fusion is considered the holy grail of energy, the breakthroughs bringing it closer to reality, and what it could mean for our future. Before we get started, if you want to see the energy revolution before it changes everything, hit subscribe. This is where fusion gets explained. The breakthrough that changes everything. For decades, scientists have been chasing one goal: creating a tiny sun here on Earth. That's basically what nuclear fusion is. It's the same process that powers our sun and every star in the universe. In December 2022, researchers at the National Ignition Facility achieved something historic. They fired 192 lasers at a tiny pellet of hydrogen fuel and got more energy out than the lasers put in. This is called net energy gain, and it's the holy grail of energy research. Why does this matter so much? Because fusion could give us unlimited clean energy. No carbon emissions. No long-lasting radioactive waste like traditional nuclear power. Just abundant energy created from the most common elements in the universe. We're talking about powering entire cities with fuel the size of a sugar cube. One glass of water contains enough hydrogen to power a home for an entire year through fusion. This isn't an exaggeration. This is the actual potential we're dealing with. How fusion actually works. Let me break this down in simple terms. Regular nuclear power plants use fission. They split heavy atoms like uranium apart, and that releases energy. It works, but it creates dangerous radioactive waste that lasts for thousands of years. Fusion is the opposite. You take light atoms, usually different types of hydrogen, and you smash them together so hard they fuse into helium. When they combine, they release massive amounts of energy. The challenge is getting atoms to fuse. You need extreme conditions. We're talking temperatures hotter than the center of the sun, over 100 million degrees Celsius. At those temperatures, matter becomes plasma, a superheated soup of particles. You also need incredible pressure to force these atoms together, because they naturally repel each other. The sun does this easily because of its massive gravity. Here on Earth, we need technology that sounds like it came from a sci-fi movie. The technology making it possible. Scientists use two main approaches to create fusion. The first is magnetic confinement, used in machines called tokamaks. These are massive donut-shaped reactors that use powerful magnets to contain the plasma. The magnets create a magnetic cage that keeps the superheated plasma from touching the walls, which would instantly cool it down and stop the fusion reaction. The largest tokamak being built right now is called ITER in France. It's the size of a building and involves collaboration from 35 countries. The second approach is inertial confinement, which is what the National Ignition Facility used for their breakthrough. They fire hundreds of incredibly powerful lasers at a tiny fuel pellet from all directions at exactly the same time. The lasers compress and heat the pellet so fast that fusion occurs before the fuel can explode outward. It happens in less than a billionth of a second. Both methods are trying to achieve the same thing: creating conditions extreme enough for fusion to happen and getting more energy out than you put in to start the reaction. Why this took so long? Fusion research started in the 1950s. Scientists have been saying fusion power is 30 years away for the past 70 years. So why has it taken this long? Because the engineering challenges are absolutely massive. You're trying to create and control the most extreme conditions that exist in the universe. The plasma is hotter than the sun's core. The magnetic fields need to be incredibly precise. The lasers need perfect timing down to trillionths of a second. Any tiny error, and the whole reaction fails. Plus, even when you achieve fusion, you need to sustain it long enough to actually generate useful power. The recent breakthrough lasted for a fraction of a second. We need fusion reactions that can run continuously for hours or days to power actual cities. Then there's the materials challenge. Whatever contains the plasma or withstands the energy needs to survive conditions that would vaporize almost anything. Scientists are developing new materials and alloys that can handle this punishment. But progress has been real. Every decade we've gotten closer. Better magnets, more powerful lasers, smarter designs, and better materials. The breakthrough we just saw proves fusion energy isn't just theoretically possible. It's practically achievable. What fusion energy means for our future. Imagine a world where energy is basically unlimited and clean. No more oil spills. No more coal plants polluting the air. No more wars fought over energy resources. Fusion changes the entire equation. The fuel for fusion, deuterium and tritium, can be extracted from seawater and lithium. There's enough in the oceans to power humanity for millions of years. The ocean is literally an unlimited fuel tank. Unlike solar and wind, fusion doesn't depend on weather or time of day. It can provide constant baseline power whenever we need it. Unlike fossil fuels, it produces zero carbon emissions. The only byproduct is helium, which is harmless and actually useful. Unlike traditional nuclear fission, fusion produces minimal radioactive waste, and what little it does create becomes safe in decades, not thousands of years. The challenge is still ahead, but we need to stay realistic. Fusion power isn't happening overnight. The recent breakthrough was important, but it only measured the energy produced at the fuel, not the total energy used by the system. The lasers still consume far more power than the reaction created. For fusion to work, the whole system must produce more energy than it uses. We also need reactors that can run non-stop and reliably. Today's machines are experiments, not power plants. Turning fusion into usable electricity means solving many engineering problems, from capturing heat to keeping reactors running safely and cheaply. Even with strong progress, most experts say commercial fusion is still decades away, likely sometime between the 2030s and 2050s, depending on funding, politics, and future breakthroughs. Why we should be hopeful? There's real reason to be hopeful. Fusion has finally produced more energy than it used, which was the biggest challenge. Funding is growing fast, with governments backing huge projects and private companies racing to build smaller, quicker reactors. Technology is moving faster than ever, making once impossible ideas realistic. With climate change increasing the need for clean energy, the rewards for success are massive. We're closer to fusion power than ever before, and the recent breakthrough shows we're heading in the right direction. What makes nuclear fusion legendary isn't just the science. It's the promise of a world powered almost endlessly, without pollution or scarcity. But breakthroughs don't mean instant results. Humanity still has a long road before fusion energy is everywhere. So tell me, do you think fusion will transform the world in our lifetime? Or is it still a dream? Drop your thoughts in the comments. If this video gave you a new perspective on the future of energy, don't forget to like, subscribe, and share it with someone who's curious about what powers our future. Thanks for watching. I'll see you in the next one.